It's a cameraman over here.
I'm so proud I've almost filled this notebook. This will be my first one.
My grades right now for statics. As you can see, 25% for what? And 10% midterm though, like I did good on that midterm. Like I studied for it. Like that kind of makes me upset to some extent. Like you know, like it's
but at the same time,
it's nice.
You just go like this.
Right?
Perfect.
It's the easiest way.
Yeah, and now I'm not spending for
I was just seeing if it's
You can tighten it a
that
little
way.
bit,
well, I'm sure he'll just give me a
or
for that. Yeah.
tighten that if it's a
Like
little bit
it's
too
so
loose.
stupid that like
and you will probably turn it into our way you submit it studying problem sets.
we already submit problem sets online. So like it
And
doesn't.
are they 100% of problem sets? No.
All right. Good morning, everyone.
Generally, don't get 100% of those.
Well, you get like
Okay, so we are moving right along here very quickly.
I'll be fine.
And
with my grade.
you remember last class we started looking at magnetic fields. Magnetic fields, and we saw that there are two sources of magnetic fields: permanent magnets or electromagnets. And permanent magnets, as we saw, was due to a bunch of electron spins, while unpaired electron spins all spinning in the same direction, and those contributions added up to give us a macroscopic field. And then an electromagnet was basically a magnet that's caused by current that you can turn on or off just by opening or closing a switch. So all magnetism is due to moving charge. Permanent magnets, it's due to a bunch of electrons pointing in the same way. And electromagnets, it's due to a bunch of electrons drifting with a drift velocity in the same direction. All right, so now today we're going to look at a few more examples, but what we're going to do is, I'm also going to introduce the Biot-Savart Law. And the Biot-Savart Law, what the Biot-Savart Law does is it kind of gives a theoretical underpinning for some of the formulas that we looked at last day. We might get to Ampere's Law by the end of class. If not, we'll definitely get to Ampere's Law on Friday. Your homework for this chapter is due next Wednesday. And our final homework will be due the Wednesday of finals week. And then your final exam will be the Friday of finals week. All right, so take out your voting cards for a moment. Let's start out with a warm-up example.
Just for clarification, you said that the final homework's due during the Wednesday of finals week. Just so we go to your office.
Final homework is due Wednesday of final week, and the next homework is due next Wednesday.
So
Yeah.
how do we turn? We bring it to your office during finals week?
You can drop it off in my mailbox.
Thanks. Thank you.
Best to just drop off the final homework in my mailbox. And that's in the main physics office. All right, so the question we'll look at here is the following is, let's say I bring a bar magnet to a non-magnet, but when I do that, it induces a magnetic field is induced in this material right here. So which configuration or configurations would be responsible for that induced field? Have a moment to think about this. So let's take a vote here. 3, 2, 1. All All right, and you might be showing more than one color. All right, now, just convince your neighbor which is the correct response or responses. 30 seconds.
Center A or C.
I did.
So I'm heading north is pushing that way, and C south is pulling yeah. From the right of it.
Wise Nancy.
Yeah, right. That's why I'm going
The
to
current goes go either way.
Electric between magnetics and No, I was just being dumb because I forgot that the geographic north is the magnetic south.
Wait.
But yeah, you're right.
Oh, I
I hope I get that. I have about a C.
Okay, and let's take a final vote here.
Yeah, I think they're.
All right, we've converged to A and C, which is correct. So, think of this material right here, which could be iron, or it could be some paramagnetic material. And a paramagnetic material is a material that becomes magnetized in the presence of a field. But when you take that magnet away, it loses its magnetism. So what's going to happen is if I have a bunch of field lines coming out of the North Pole, like this, it's going to cause all of these randomly orientated magnetic dipoles. Think of them as electron spins. They all want to torque to line themselves up with the field. Similarly to how an electric dipole wants to torque to align itself up with an electric field, a magnetic dipole wants to torque to align itself up with the local magnetic field. And each individual electron that's unpaired in an orbital is like a little magnetic dipole. If we picture it as a little ball of charge, which is spinning, a little north pole, a little south pole, that little dipole would orientate itself in that direction. So A and C would both. It's like a little compass needle. All the little compass needles pointing in the same direction. That's what an electron is really. It's a little compass needle. All right. So last day we looked at currents, and we looked at the magnetic field due to a current, and we found that magnetic field due to a long wire is mu naught I over 2 pi r, where r is the radial distance from the wire. So we'll see where this comes from today. There's a couple ways that we can get to this equation. But as a warm-up exercise here, let's say I have two parallel currents that are pointing out of the board like this. Question is, what direction does the net magnetic field point right here? So take a few seconds quietly, and I'm going to have you vote the direction that the net magnetic field points at this dot right here. Up, down, left, right, in, or out. Just thinking quietly at this moment. Okay, let's take a vote. A, B, C, D, E, or F. The two currents are coming out of the board. And I'm asking for the net magnetic field at this point. What direction does it point? Okay, 30 seconds. Convince your neighbor. Direction of the field right here.
That's kind of what I was
Right there. Yeah.
So that's like that. Yeah, it's like this, and then like Well, one of them's going like this, right? So it's like
Yeah,
this.
because one's
going
coming around this way, one's coming that way.
They're both good. The point is on the right side has the right.
I guess,
They're both
Some
I just
both your hands.
find like,
Draw back like this. That way. So it's like this. You can see this one comes through the top one, going out that way. Like, net down.
Okay, get ready to vote again. Prepare your vote. And we'll take a vote here. 3, 2, 1. You have a majority B's, which is correct. It does point down. The reason it points down is because if I take my right hand for the top current and point it in the direction of the current, the field wraps around this way. So imagine a circle of constant radius. The field due to the top wire points like this. Now the bottom wire also has a field that wraps around it. And I can imagine a circular arc like this. Now what's going to happen is the net field is going to point directly down. So we have the magnetic field to the bottom and the magnetic field due to the top. All right, now, same question, but over on the very right-hand side. Give you a moment to prepare your vote. What's the net magnetic field? At the very right, on the very right point.
Yep, I agree.
And let's take a vote on 3, 2, 1. Yeah, it's just going to be the opposite. It's going to be pointing up now. So now, if I look at the magnetic field, if I continue that circular loop, the magnetic field due to the up, due to the top, 1 point kind of angled to the right and up, and then due to the bottom loop, I have a magnetic field that points like this, right? And because of the symmetry, we're going to have a net magnetic field that points directly upwards like this. Can anyone tell me what the field is right at the very center point? 0, because now they cancel each other out. Exactly. Going to be 0 right in the center because the two fields will be pointing in the opposite direction and they'll have equal magnitude. So they'll cancel each other out exactly. All right, so same question now, but let's say I change things up a little bit and I say, actually, let me do it this way, is, so last day, remember, we looked at a loop of current, and a loop of current produces a magnetic field. So let's say now that I stack some loops. So I take one loop that looks like this. Now this is an edge view. So the current is coming out and wrapping back around. For this particular loop, current is going like this and then into the board. So the magnetic field, as we saw, looks kind of something like this, due to that one loop pointing to the right inside the loop, and then outside the loop it loops around back to the left. So what happens if I take another loop and I stack it next to it? It has the same radius. Let's say those loops are wired together. Now, consider the points inside here, right on the axis, here, and there. Okay, so same question here, but what direction does the net magnetic field point at that very center point? Right here, from those options over there, what direction does the net magnetic field point? Give you a moment to choose your vote.
What did he say? Directions you made it, that
Okay.
point, the middle point.
30 seconds, convince your neighbor. Direction of the magnetic field right here with both of the loops stacked together.
Isn't it 0? Just like there. All of them are straight.
Like they sort of stack up anyway. We got
Because the like one on the bottom, and on the right we do it not, and that one's gonna get down, right? All the right?
Yeah.
As the wires components cancel out.
It behaves as if it's two, if it's one, like one loop, but then you just stretch it out. It's just going to change the curve.
Okay, get ready to prepare your vote.
Yeah,
Like this.
the more loops you add, the reason they give
Okay, 3, 2, 1. 4, I'll take to be D. Yeah, D is correct. So it points to the right, because those two loops, they both produce a field that points to the right and they add together. They don't cancel together. Because think about this left loop for a moment. If I'm on this side of the left loop, the field still points to the right when I'm inside. So the net field in the center points to the right. All right, now you can see though that the field, what would happen if I stack a bunch of loops and I continue to add the loops in. Say I take one loop and I just add a bunch of loops. So the current is flowing out at the top, in at the bottom. What the magnetic field is going to do, the net magnetic field, is it's going to stretch out, and you're going to get a field right along the axis that is straight. So it's very much going to look like a dipole field that's just been elongated. So we call this a solenoid. Solenoids are the magnetic equivalent of capacitors. You can create large, constant magnetic fields. Imagine in the limit where that solenoid went to infinity, and the loops were more tightly and tightly packed together. That field inside would become completely uniform inside, and it would have a value which will work out later, mu naught n I over L, where L is the length of the solenoid. There are n turns, and the current for each loop is I. Notice something interesting about this expression here is it's independent of the radius. Right, so this loop, these loops have a certain size, R, but the magnetic field strength inside is independent of R. Now the reason for that is if I have a really, really big loop with the same amount of current, there's more, when I'm at the center of that loop, the magnetic field is weaker, right? The magnetic field is weaker. Remember, the magnetic field at the center is equal to mu naught n I over 2 times R. That's the magnetic field at the very center. So it's weaker when the loop is bigger, but you have more of it. So those contributions, you have more current to produce a magnetic field, but you're farther away. Those contributions perfectly balance each other out, and you get a constant field when you're inside the solenoid. So this is the amount of magnetic field when you're inside an infinite solenoid with an infinite length. Question?
Vector or scalar?
Well, it is a magnetic field is always a vector. Here I've written just the magnitude of that vector.
Oh, okay.
So in this case, it points to the right, but if I was to reverse the direction of the current, it would point to the left. The direction we determined by the right-hand rule. Okay, so let's try an example question.
If it's an infinite L, how does that work? Because wouldn't the magnetic field go to 0?
Excellent question. But the number of turns, if it's tightly packed, would also go to infinity. So those two, really, another way to write this equation is mu naught n I, where n is the number of turns per unit length. Right, it tells us how tightly packed those wires are. Right, so if the cylinder was in fact infinite, you wouldn't want to measure it and then count all the number of turns, because there's an infinite number of both. But the idea is, in that limit, when you take the ratio, it's something finite. Good, any other questions? Okay, so let's look at another example here, and take out your voting cards. We'll look at, imagine I take a current loop, and I put it right next to a bar magnet. Now, they repel each other. So I want you to tell me what direction the current is flowing through that loop. And think quietly for a moment. Does anyone need more time? Okay, let's take a vote. Get ready to prepare your vote. 3, 2, 1. All right, let's take a moment to convince our neighbor of what direction the current in that loop is flowing.
So if the magnetic field is pointing that way, put your thumb on that, at the very top, it's going to be going in, at the bottom it's going Oh, that's what I intended to answer. I just got confused by the
Lines, so if they're coming in,
two clauses.
then the south is closer and it's going to get repelled.
Yeah.
So the current, this is current.
B.
Are those lines
Like, what are those magnets?
the magnetic.
Right?
Okay, get ready to prepare your vote. All right, and 3, 2, 1. Yeah, we've converged to B, which is correct. In order for these two to repel each other, the right side of the loop has to function like a south pole. And the only way for the right side of the loop to function like a south pole is if the magnetic field lines are converging into the right side of the loop. The only way for that to happen is if the current goes like this. So that inside the loop, the field lines are converging like this. Okay, so this side has to be south, that side has to be north, and then they repel each other. So that loop, here we have an example of a permanent magnet repelling an electromagnet, which is just the loop. Okay? A loop of wire. And a solenoid is just a bunch of loops of wire that are stacked, not on top of each other, but over a length. Okay, so let's take this solenoid that I have here and view it from another direction. let's say, oftentimes what we do to increase the strength of a solenoid is we put an iron core. We take an iron core. An iron is ferromagnetic, meaning it can be magnetized in the presence of a magnetic field. So we take this iron core and we wrap it with wire. Okay, so let's imagine I have current coming around here. Now, just like putting a dielectric into a capacitor beefs up the capacitance, putting an iron core into a solenoid basically beefs up the magnetic field. You get a stronger magnetic field. Actually, I could connect this to any, well, I could really make the current go in any direction here. Now let's say that I had, once I measured the magnetic field, I found that the magnetic field inside the solenoid points up. So viewed from above, the current flows. Does the current flow clockwise or counterclockwise? Take a moment to think about this quietly. What direction, if I'm looking down on this solenoid from above, what direction does the current flow? Clockwise or counterclockwise? So let's take a vote here. Get ready to prepare your vote. And 3, 2, 1. All right, yep, you got it, counterclockwise. Current would flow counterclockwise, which would mean, does the current come into or out of this wire? You know, this wire right here. Is it flowing to the right or left?
Right.
Yeah, it's coming this way. So our current is going this way and moving this direction.
And that's conventional current?
Yeah, current, we're always speaking of conventional current. Whenever we say I, it's the flow of positive charge, or it's how many coulombs per second past the point. Yes?
Wait, how did you figure out that it flows counterclockwise?
So if I use the right-hand rule, let's just say on the bottom stretch of the wire, inside it produces a field that goes up. So that would be this upward field. The current has to be going this way as it wraps its way around the loop. Just by the right-hand rule. Thumb is current, fingers curl in the direction of the magnetic field. Okay, now we can do various combinations of currents because we know that magnetic field also obeys the superposition principle. So if I have a current, let's say it looks like this, and it makes a loop of radius r. If I was to ask for the magnetic field at the center, well, the way that we would do this is we would use the superposition principle. We would say, okay, the magnetic field at the center here is due to the long straight wire and the loop. So the magnetic field at the center here has to be the magnetic field due to the wire right? And the magnetic field due to the wire is going to point into the board on the bottom side. And then due to the loop, it also points into the board. So we have B due to the loop. And we could plug in numbers there to get an actual result. But here what we're doing is we're using the superposition principle. Okay, so I mentioned how the source of magnetic field is moving charge. So let's get now to the underlying equation. And historically, this equation came later in terms of understanding the magnetic field strength. So this is called the Biot-Savart Law, which is what we'll look at next. So the Biot-Savart Law is the magnetic equivalent of Coulomb's law. Or put another way, the Biot-Savart Law is to magnetic fields what Coulomb's law is to electric fields. And what it says is if I have a positive charge plus Q, we know that plus Q creates an electric field. We already calculated what the electric field due to Q is when it's stationary. That's Coulomb's law. But I mentioned that Coulomb's law doesn't work for charge that's moving. A moving charge still produces an electric field, but the expression is not quite as simple as Coulomb's law. But a moving charge also produces a magnetic field when it starts to move. So if this charge is moving to the right at speed v, it's charge in motion. So charge in motion produces a v field. So the Biot-Savart Law tells us what that is exactly. So imagine I want to know the magnetic field here at just some point in space. Well, just from experimenting with magnetism, we could kind of guess what it has to be. We'd expect the magnetic field to be weaker as you get farther away from the moving charge. That kind of makes sense. If I was infinitely far away from moving charge, I'd expect there to be no field. If I was really close, I'd expect it to be really large. So it's going to depend on this distance r. And I can label a small vector here, which I'll call r hat. R hat is that unit vector which points from the charge to the point that I'm interested in. So the magnetic field due to this point charge is equal to, this magnetic constant comes into place here. Now there's this factor of 4 pi, which also appears. It should be proportional to Q, right? More moving charge, the field should be stronger. It should also depend on how fast the charge is moving, V. Put a vector sign here because magnetic field is also a vector. It should also depend on direction. So it turns out that V cross R is a cross product which gives me a vector that's perpendicular to V and R. So if I take V and cross it into R, roll it into R, I get a vector that points out of the board. So my magnetic field at B is actually going to point out of the page. So we know it does point out because V crossed into R gives me a vector that is perpendicular to both V and R. And depending on the distance, there's going to be an R squared here. So it gets weaker. It falls off as 1 over R squared as you get farther away. So again, it's still a 1 over R squared law. Now this is not something I derived, but you can think of it as this is a law which was discovered. And you can't prove to be that it's true, but it turns out that this is the way that magnetic fields behave. So if I was to write just the magnitude of this equation, B due to the point charge, mu naught over 4 pi, and I would have Q, V, sine theta over R squared, where theta is that angle between R hat and V. Now notice some interesting things about this equation. If V is 0, there's no magnetic field, which is what we expect. If r goes to infinity, there's also no magnetic field, because you're really, really far away from that charge that is moving. So this is for a single point charge that is moving, but if I look at a current source, I can actually, for a current, I can take the QV and I can replace it with an I delta S. QV goes to I delta S because current is just charge per unit time multiplied by a distance. That's like charge times velocity. This is just the equivalent. When I have a bunch of charges that are moving all together, I don't want to count all the individual electrons that are drifting. I'll just talk about the current instead. This equation also works if I replace QV with I delta S. Question?
What is that?
S is just a small length of current. So if I have a current that's moving in this direction, delta S would be that small little vector that points in the direction of the current at that point. Yes?
What would the magnetic field line look like for B out, like coming as around a circle around the charge? Would it be, would the circle be totally, like from this perspective, totally just straight up and down, or would it kind of go around the charge?
Okay, good question. It's kind of hard to draw here, but the field due to a point charge would circulate around the charge. So it would let's see if I can, it circulates around the charge like that. Because we'd expect if it was a bunch of point charges lined up in a row and they're all moving to the right, we know the field wraps around. But just a single point charge, what's going to happen as you come over here is the field just gets a little bit weaker. Because R is getting larger, so the field gets weaker as you get farther and farther away from the point charge, but it looks the same shape as a current. A current is a bunch of point charges all in a row and they're all moving together. So just like the solenoid stretches out the field into a single loop, a current is a bunch of point charges that are stacked and they're all moving together, which makes these have all the same radius. Yes?
Isn't current and delta S going in the same direction?
Correct.
So wouldn't the theta be 0?
The angle is between, the angle is going to be between current and R.
Oh, current.
And typically we just assign the vector to the length element instead of the current.
Okay, okay. Yeah.
So what happens then if I have a really long, let's just do that. Let's just apply this equation to a really long current, right? Which is just a bunch of positive charges that are moving. That wire again is not charged though because we know that it's current or current in a wire. It's an uncharged wire, but it's a bunch of charges that are just drifting through the wire, right? So let's say we have a long wire, and I want to find the magnetic field due to that wire. We're just going to use the Biot-Savart Law. And now it's going to look very similar to Coulomb's law. We're just integrating or adding up a bunch of little pieces. So if I have a long wire, and let's say my wire looks like this, and I'll say the wire is carrying current I. And let's say I want to find the magnetic field up here at some point P. Now we already know by the right-hand rule the field will point out of the board. We already know the field at that point points out. But let's work out the strength due to the field. Now this is a long wire, so it goes really long on each side. So the first thing I need to do in order to apply Biot-Savart Law is choose a coordinate system. So So I'm going to choose a simple coordinate system. I'm going to choose one that's has its y-axis in this direction and its x-axis here. And the magnetic field to do this long wire is complicated. So let's use that strategy that we've been using for Coulomb's law and break the current into a bunch of little chunks. So here's a little chunk of current. Now this chunk of current has a certain length. And I'm going to call that length dx. And that chunk of current is a certain distance from the origin, x. And the magnetic field is a certain distance from the origin, which I'll call y. So the distance from the charge that is moving, which is this little piece right here, to the point that I'm interested in is r equals the square root of x squared plus y squared. Now here's my little r hat vector. And here's my little dx vector. So what the Biot-Savart Law says is, if I take the cross product of dx and r, I'm interested in the angle between the two. So I'm interested in that angle right there. Now let's do a little bit of geometry here, because the sine of theta is really what we're interested in. Sine of theta versus theta looks something like this. Familiar with the sinusoidal graph? Now, this angle is actually greater than pi over 2, but it's less than pi. So that angle actually corresponds to somewhere here. So the sine of theta, actually in this case, is going to equal, symmetrically, it would also equal this point right here. It would equal the sine of pi minus theta. And pi minus theta is this angle right here. So that angle right there is, in fact, pi minus theta. So this is just geometry so far. We're just sketching out our configuration. It's always important to add a coordinate system, label your angles, label your distances, and now it's really just mathematics takes over. If we set our problem up correctly, we just plug in the numbers. So the magnetic field, I'll say the small magnetic field, due to a little chunk of current, is just mu naught over 4 pi. All right, and then next, my QV, I just replace with an I ds. So mu becomes I dx, and then the r squared becomes x squared plus y squared, to the 1/2, and this is all squared. And the sine theta, which is the same as sine of pi minus theta, is equal to, geometrically, sine of pi minus theta is going to be opposite. So it's going to be y over square root of x squared plus y squared. So I have a y, and then I have a 1 over x squared plus y squared to the 1/2. So combining this all together, I have mu naught I y over 4 pi, 1 over dx over x squared plus y squared 3/2, integrating from, well, to get the total field B, I have to add up all the little chunks. And I'm integrating here from -infinity to infinity, would give me the magnetic field due to the long straight wire. Okay, now here's where, now can anyone tell me how we would do this integral? Anyone remember any techniques from integral calculus to solve an integral like that?
Would we have to parameterize that?
What do you mean by parameterize?
Like find x and y in terms of t?
Well, we don't have to do that. We only have to do that for line integrals, so we wouldn't have to do that here. Yes.
Well, I know for the limits of integration, you'd want to change those into like an A and B and evaluate them as the limit of A or B to infinity. But for the integrand,
All right, so I'll let you think about this. From integral calculus, how you would solve an integral like that.
Use a trig sum.
Maybe try a trig sum. So the answer comes out to 2 over y squared, which means our magnetic field due to the wire is equal to mu naught I over 2 pi y, right? Which is exactly, that's exactly the formula I wrote down for you earlier, but that really comes from the integral, from the Biot-Savart Law.
So
Yes.
how could problems like this look like on the final?
So we'll do a couple examples of what potential problems you could get. Because what are some basic geometric configurations we could have? Well, one of them is a line of charge, which I just did. But imagine, which is a current, but imagine stacking up a bunch of lines of charge. So, which I'll do an example of now. Okay, so we'll end here with an example, but then we'll pick up with this next day. Is imagine what possible simple geometric configurations could we have? Well, I could potentially, we could have a current of finite length. That would basically be the same thing here, but changing the limits of integration. So if you had a finite length current, right, you can find the field at these different points. For instance, around the current. Another thing you could do is, so here's a finite current. You can also have a sheet of current. For example, I'm just thinking of possible ideas here. Right, and a sheet of current would just be a bunch of individual currents coming directly out of the board, right, or they could be going directly up. And I could ask you, say, what's the field here or here around that sheet of current. If we consider this to be really smooth, such that the sheet of current had length L and it had N wires, you could find the magnetic field all around that sheet of current just by knowing what the magnetic field is due to a wire. So you would take this result and you would add it up. Integration and summation, you'd add it up a bunch of times for all these currents that have different distances from that point right there to do that. So I'll do an example of this next class, but let me show you one other possible example which you could possibly use is Or what other examples could you possibly have? Well, the Biot-Savart Law applies, it's really how you find the magnetic field due to a loop of current of radius r. Right, applying the Biot-Savart Law to a loop of current. The textbook does this, and you'll want to review this. U naught over 2 I, so we use this formula in laboratory, I r squared z squared plus r squared to the 3/2. Or here's my z-axis. And I can ask, what's the magnetic field at any point along the axis of that loop? Okay, now what can I do with loops? I can combine a bunch of loops together to get a solenoid. So, solenoid of finite length. A solenoid of finite length really just looks like this. Has length L, has n turns, and we could use, as soon as we know the magnetic field due to one loop, we could then really use the Biot-Savart Law and integration to find the magnetic field at any point along the z-axis. Because for a finite solenoid, the field is going to be strongest at the center and weakest at the ends, just like there's a fringe effect due to a finite capacitor. So same thing for a solenoid, the field lines actually bend away on the outside, which means the field's a little bit weaker, and the Biot-Savart Law would allow you to figure out what it is just by adding up a bunch of loops that are different distances away. So we'll try an example of this next class, and then we'll also discuss Ampere's law. And Ampere's law gives us a simple way to calculate magnetic field, just like Gauss's law gave us a simple way to find electric field.